one should be careful which things to ignore. Sometimes you can ignore certain things, some things you don't. It's really up to the engineer.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Dave Finch. Today we're talking about power electronic design for automotive applications with some heavy-hitting experts, a senior engineer from Tesla and an applications engineering manager from Vicor. As automakers continue to invest in electric vehicles and in increasing the electrification of their gas and hybrid models, the demand for power electronics in the automotive sector has never been stronger. It's an interesting proposition for engineers. Take the noisy, heat-generating world of power electronic design and marry it harmoniously with the harsh and unforgiving world of automotive specifications. Today, we'll visit with engineers from two innovative companies that have taken substantial leads in developing novel power electronic solutions for the automotive industry. Paul Yeaman is Director of Applications Engineering at Vicor. The company is producing some of the most interesting power supply modules on the market. Paul shares his perspective on designing robust power converters.
If you can limit or eliminate switching losses in your power converter, now you've solved this trade-off between switching frequency and switching losses. Now you're able to make things much smaller and get the benefits of efficiency.
But first, you may remember that we recently spoke with John Wenchow, Applications Manager at Wolfspeed, a Cree company, about the role of wide bandgap semiconductors in power applications. In case you missed it, here's what John Wen had to say about the automotive industry's earliest adopters of silicon carbide technology.
2 years ago, Cree had a survey for those major EV company. How many are willing or plan to make the transition to use silicon carbide? Even 2 or 3 years ago, only one company was working on that.
Really?
Which was Tesla.
Okay. Most of us weren't surprised at all to learn that Tesla was the first major automaker to adopt a technology that pushed the boundaries of automotive design. So today, I thought it'd be cool to chat with one of Tesla's own power electronics engineers about taking part in such an exciting ride. Milovan Kovacevic holds a master's in electrical engineering from University of Belgrade and a PhD from Technical University of Denmark. He's been designing power electronic systems professionally for about 6 years, and most recently, he's been tackling power conversion challenges at Tesla.
First challenge is optimizing the design, but probably zeroth challenge is to find specifications. Finding and interpreting specifications is the first challenge. Then the specifications get refined, and you hope that they will always be inside the specs that you had from the beginning, but they never are.
Yeah.
And sometimes they change after you design it. But that's just what happens. Another challenge, converting high voltage to low voltage, is typically needs to happen through a transformer, and designing the whole converter to deal with simultaneously high voltage on one end and especially low voltage and high currents on the other end is challenging. Essentially, that transformer design is critical. For your success in this case. You could say this converter is essentially nothing. It's not so special. I would say there are certain things that are kind of unique to it. So picking a topology that will work for your design is another layer of complexity. Designing the transformer, how many turns on each side?
Right.
That's another complexity. How to maximize magnetic coupling and how to minimize capacitive coupling is another challenge. Capacitive coupling from one side to another will result in EMI emissions.
Mm-hmm. And what are the sources of that capacitive coupling?
Generally, pieces of metal being close together and their potentials moving independently.
Yeah.
That's like as general as it can be. There, the capacitance is always there where if you have pieces of metal, but if they move simultaneously, there is no current between them. So what you try to do is arranging windings one way or another way. Capacitance will be probably the same, but how much the potential changes between the two depends which specific windings in the transformer you put close together.
Yeah.
So you want to kind of avoid placing the high DVDT windings close to the secondary side. Or of course, it has to be small. It has to be light.
Yeah.
Ideally, it should not heat up at all. And so
It'd be nice.
But yeah, we go back to essentially. Let's put all the math together and see what it gives out as the best design. And I would say one should be careful which things to ignore. Sometimes you can ignore certain things when you try to do some kind of global evaluation of the design space. Some things you don't. And it's really up to the engineer to figure out what is their target.
Yep. If the marketing people say, well, you know what, we actually wanted to add the ability to have all these different dimmable LEDs inside the car, well, that completely changes now your DC to DC design.
Yes, in some sense, yes. So I think my supervisors have seen a fair share of it and tend to aim at the higher end of the specifications, so that we kind of say, okay, so we have these specifications today, but we are so gonna have these different specifications tomorrow. Yeah. Let's aim for tomorrow, and justify that by thinking about future and thinking ahead. And if anybody pushes back, then we told you.
Yeah. Right.
So this is why this actually leads us to another question: what kind of switches do you use? And for example, inverter design and
yeah, exactly. And that's the thing. It was always power MOSFET, and then IGBT technology came along, which offers the best characteristics of the MOSFET, but then the power handling capability of a bipolar transistor. And
MOSFETs are, as it turns out, from physics standpoint, they are very easy to turn off. The time to turn off can be really small compared to bipolar devices. And that essentially reduces turn-off loss. When do you want to use MOSFETs? You want to use MOSFETs, in comparison to IGBTs, until a certain point. They are better in every way. When we talk about higher voltage and say inverters, when you have when you're increasing current, your MOSFETs are better, but until a certain point, there is a crossover with conduction loss with IGBTs. The reason is resistance across the device is higher in MOSFETs, but in IGBTs you have an additional voltage drop from fairly fixed voltage drop across it, which goes on top of the resistance.
The collector to emitter drop?
Yes.
Yeah.
At certain currents, it becomes more advantageous to use IGBTs. One thing which IGBTs force you to do is to run at lower frequency because they have large turn-off loss or large switching loss compared to MOSFETs.
Which definitely is a big factor in how you're driving the motor.
Yes. Running at lower frequency increases current ripple in the motor. So you have more conduction loss in the windings. And really when you're designing a motor, you don't want to be very conservative, because that will result in a large and heavy motor. In EVs, that means shorter range. Yep. So what you do is you do a lot of testing, you do a lot of evaluation of the motor performance, and you're designing motor to hit the limit, but not overshoot a lot.
Yeah.
Depends, of course, what your limits are, and like what is it that you are aiming for. But let's say, like, if you know your performance ahead of time, that determines essentially how much you can push the motor in terms of conduction loss or otherwise. Then that determines that essentially drives the inverter design.
So so your design factors not only are going to be the voltage and current that you need to be able to handle, the switching frequency that you're designing for, the modulation technique, and also you're designing, and this is true whether it's an inverter, a small DC to DC regulator, whatever the case is, in these power applications, one of the biggest design factors will always be thermal issues.
Absolutely. So what happens when you're trying to optimize your design, you're trying to make it smaller or lighter. Specifically for commercial vehicles, that is, like, you want light motor. You don't want more weight. Generally, you also want less volume, but it seems to me that volume is less constrictive than weight. Mm-hmm. But these things generally tend to go along together quite well. So yeah, you want to have a smaller motor, ideally with a simple manufacturing process, which does not cost a lot. Automotive very sensitive to cost.
Right.
Yeah, you want to pay as little money as possible. You want it to be more efficient because that means a longer range. And these are contradicting requirements. So what happens is there is an optimum. And you want to find that optimum where you push, and of course, like as the size grows smaller, temperature tries to go up. Also, as you try to go smaller, it's very typical that efficiency goes down, unless like you're doing some, there is again somewhere there is an optimum, and you are looking for that optimum where how you can like squeeze everything together. So one, like you mentioned thermals, and that is absolutely correct. The thing is, it doesn't help to install too much cooling. In certain cases, it doesn't really help because you actually need efficiency. You could potentially keep the temperature low, where semiconductors and capacitors will operate properly. But it doesn't really help because you're reducing the range.
I see. Yeah. So exactly. It's almost like a Band-Aid. Like you can solve kind of one smaller problem, but you're not really addressing the main issue, which is if you design it for efficiency.
And your audience will totally understand this concept. It just does not, there is too much of a good thing. Yeah. In some sense. And what that means is like, yes, you're overpaying the thermal system, and you are underpaying the actual converter design or the motor design. So,
and it's interesting when I think about efficiency and I think about losses in a power circuit. I always think about it in terms of the thermal characteristics of the semiconductor devices. But certainly you have to look at holistically, you have to look at the entire system, including the passive devices as well. You can't just design one part of the circuit for high efficiency. It has to be, you're designing the entire circuit, all components of it together, you're designing for the best efficiency.
Yes. So one thing you can always, like if you don't want to do global optimization, you can start somewhere and see how things move when you try to like scale it one way or the other. Mm-hmm. That definitely applies to magnetics design. You can design magnetics to be too efficient, or in that sense too large, or like larger than they need to be. Every part of the circuit contributes to the performance and the performance hit. So ideally, you want to see how all of that moves together.
And then I also have to think that your control firmware also plays a part in this because you have to react as quickly as possible to changing conditions.
In some ways that is true. In some other ways it is not true. You should react quickly to changing conditions. You should be very careful about interpreting the results, or not allowing false events to command what's happening in your firmware. Because one thing that switching circuits are notorious for are noise, and that noise comes in at every switching event, and it's sometimes really hard to predict where it's going to go. So hence, when you do the design, you do your best to assess how and where noise is going to propagate. Generally, you want to contain it because of system level implications. You don't want to let radio listen to your switching noise.
Right. Yes.
Just like some things that happen generally that happens in industry, and every engineer goes through this, or power electronics engineer goes through this phase of, okay, so I'm done with designing just an optimal converter. I need to consider other things too. Yeah.
So my only familiarity with control algorithms in a power system would be just PID controllers.
Our automotive sector loves PIDs. They are very predictable. They will do. They're very easy to simulate. Very easy to predict how they will behave. That and as people call this, burst mode control. That control mechanism is really easy to build and implement, and it just works like a charm. Automotive industry really appreciates things that are known to be stable or can be proved to be stable.
EPC is the leading provider of gallium nitride-based power management technology and is doing more than just improving efficiency of electrical power. It is also enabling new, life-changing applications that didn't exist 5 years ago. Applications such as LiDAR for autonomous cars, robots, drones, and security systems, RF envelope tracking for 4G, LTE base stations, and low-cost satellites were some of the first to take advantage of gallium nitride's high-speed switching. Now, high-volume applications, including those for data centers and automotive, are recognizing that gallium nitride is the preferred technology for progressive companies eager to remain at the forefront of their industries. For more information, go to epc-co.com.
What are some ways that engineers can either contain or minimize the amount of noise that will be produced in a switching circuit such as this?
Right. So one thing is being able to predict what your sources are is really good. At least give it a try. So even at the circuit design level, you can do a lot, especially if you consider that you will have parasitics and you don't neglect the ones that you are afraid of including. Experienced inverter designers would know from a get-go where noise is going to go, and what are the sources of it, and how things will unfold. One way to contain switching noise from all converters is adding filters on the inputs or outputs of the converter. In the case of the inverter, there is really no need for output, because output is the wheel.
Yeah.
But the noise generated by switching events in the inverter, they will definitely try to go wherever they can, and so you build enclosures, you build filters, EMI filters as they call it, and if you were good at predicting what you will generate, you will have a chance at containing electromagnetic field or the currents that you generated in the process.
Yeah. And this is radiated noise. Is it also conducted into the copper?
Both. So you will certainly have conducted emissions, and that is easier. It is still a hard problem because in the sense that you have to pay something to suppress conduction noise. Mm-hmm. And that is and generally like inverters, when especially high power inverters, they will have low operating frequencies. You need big magnetic components and big capacitors to suppress this noise of theirs. And again, like I say, that is an easier part, one that will not really sneak up on you. You know this is going to happen. You have some vague idea that some people have better ideas than others, right? That you will have also radiated emissions because there are really fast voltage transitions. There's a 30 megahertz limit until which we measure conduction emissions, and above 30 megahertz, we measure radiated emissions. Okay. If you suspect you will have high frequency currents above 30 megahertz, you have to deal with that as well. To contain those, layout is essential. It was essential also for conducted emissions, especially at higher frequency range. And what it means is if you're drawing your circuit and you have a trace somewhere that's going to have some inductance, which means like at some point energy from there needs to stop flowing or needs to move somewhere else. Whenever that happens, usually happens at the beginning of switching events. It will try to go somewhere else. Ideally, you either dissipate it somehow. So you have people build snubbers, which generally either slow the transition edge, or provide a path for these currents to flow, and then dissipate those. So those snubbers will be lossy typically. It's like an RC snubber, that is one way of dealing with some of these issues, especially radiated ones. And another is layout. Careful positioning of planes or nodes which will experience this high voltage, high DVDT as they call it, high voltage per second events. Yeah, so you try to kind of contain it that way. So you surround it either with an enclosure, and then you go to the lab and some EMC engineer tells you that you did it all wrong, and you go back. I have to say, like how I imagine the converter design to be and how it seems it is completely changed from the time I graduated, especially like at these high power converters which you don't have like application node to build off of. I see these two branches essentially happening. So numerically speaking, a overwhelming number of converters are essentially trapped in application nodes designs, and certain converters will be that are made custom. That's actually three branches now. But it's like you could say like for really high volumes, you want to do as good a job as you can at like reducing cost and like fitting, making a good design of the converter. And there's going to be always something in between where, especially like when you don't have a lot of volume, the cost is not as critical, but that is just like what a typical engineering story. Yeah. If you have some volumes, then then you take this route. If you have different volumes, you take this other route, and yeah.
What do you think was some of the biggest surprises between what you saw the industry or what you saw these applications as and what they actually are?
I think my biggest surprise was in controls. and the importance of controls in power converters in the sense of control laws and modulation schemes and so on. There is a general tendency in industry to go with simple or simpler approaches rather than more complicated ones. There's a slight difference between complex and complicated.
Yes,
Python
definitely.
programmers know this the best. If it has to be complex, yes, then then that's all right. If it's needlessly complicated, then if you're saving 1% or 0.1% of the cost, but you have to have way more complicated control scheme, it's generally not worth the money.
Yeah.
And another thing is, really, what is important is that you optimize for cost. Overall cost impact, you would say, like not just how much it costs on paper, but if I take this route, what does it mean for the system?
Mm-hmm.
If I optimize this circuit, but I completely disregard the rest of the vehicle, does it mean that there has to be now some different circuit to do certain additional function? It is definitely more complicated than just like in academia, there's typically a lot of papers that talk about control laws. And I just see that like in industry, very few people care about that. They want better magnetics. They want better capacitors. They want better switches. And they just want to keep rolling what is already known. Very few, you could say, very low percentage of papers become relevant in industry.
That's interesting because there are superior options, but design teams get locked into a couple things. The way that things were done before. And so, there's sort of an inertia that's involved with trying something new and proving something new. I think sometimes it is easy to look at, well, we will increase the system cost by having to use a more sophisticated microcontroller or a DSP or an FPGA. But by introducing a smarter control algorithm, we can actually potentially shrink the amount of copper that's needed in the motor or the magnetics, and achieve an overall cost optimization. But then in the real world, something that I think in academic papers that doesn't get addressed is that in the real world, there's also the supply chain to consider. So you have to convince a buyer to look at new products and new solutions that they haven't approved before. And sometimes there can be a challenge there.
Absolutely. We see that very often. New components, and especially if they are single sourced, it is almost like this is a forbidden fruit. You shall not reach out there. That is definitely what our supply chain prefers not to have to deal with. That's one reason, single sourcing. But also, if it's a new technology, it is a question of reliability of that new component, which had not been tested for like millions of hours in the field.
This segment of our show is sponsored by Eaton's Electronics Division. Need energy storage solutions for your design? Eaton has a broad supercapacitor product offering, ranging from coin cells to modules. Eaton's online resources and experts can support all of your design needs from ideation to production. Learn more about Eaton's ultra-high capacitance devices by visiting www.eaton.com/supercapacitors.
Welcome back to the lobby. If successful power electronics design for automotive applications comes down to power quality, thermal performance, noise characteristics, and size, then it might be worthwhile to look at the pros and cons of power modules. Paul Yeaman, Director of Applications Engineering at Vicor, sheds some light on these highly efficient, regulatory compliant solutions for high and low voltage automobile electronics. When I start thinking about, let's say we're starting from a very high voltage battery, we're going to down convert to 48 volts. Second would be 12 volts, and then on and on. But immediately I start thinking about, boy, that's every time you do that, you're introducing losses. For electric vehicle applications, I start thinking about shorter range on the vehicle, I also start thinking about additional weight. Something I've noticed is that your switching converters are achieving like upwards of 96, 97% efficiency.
Yeah, first of all, one of the reasons behind going with a higher voltage, 48 volts as opposed to 12 volts, is to limit distribution losses, which are the resistive losses that come about by pumping high currents through an automobile chassis or any kind of a system. The trade-off going to a higher voltage is you now essentially need to down convert to that voltage. So the important thing is that your conversion losses need to be less than the losses that you would incur by distributing that higher current at that lower voltage. That represents essentially the trade-off between, do I pump 12 volts throughout the entire system, or do I store energy at 48 volts and down convert to 12 volts? That represents kind of where does it make sense to do one versus the other. To talk a little bit more about the 90, 97% and 98% efficient converter, one of the ways to make that trade-off more favorable towards convert as opposed to distribute the lower voltage is to basically push your technology to higher and higher efficiency. Now, in some respects, there's some things about power conversion technology that's never going to change. One of those things is copper. There's no such thing as more efficient copper.
Right.
There are some things that are changing, quite rapidly. And in that category, I would put MOSFETs. MOSFETs, if you take, for example, silicon MOSFETs, and you look at some subsequent generations of silicon MOSFETs, they continue to get lower RDS on, lower gate charge, which means higher figure of merit in terms of being able to switch them more efficiently. If you look at emerging technologies like silicon carbide and GaN, you have a step change in terms of performance with some of these emerging wide bandgap devices, which I'm sure you've heard very much, and I'm sure you've even had podcast guests that talk a lot about the advantages in wide bandgap technology. So on the MOSFET side of things, there's a lot of innovation and there's a lot of development. Where Vicor fits into that is where Vicor looks at innovating is kind of at the topology level. So in other words, we take advantage of emerging and better MOSFETs with each subsequent generation. But what we also do is we look at how do we more efficiently convert or regulate the electricity from one voltage to another. So we're looking at things like control of power topologies, things like zero voltage switching and zero current switching, which are control techniques which allow you to turn on and off a MOSFET, at a point where you minimize the switching losses. Magnetics, magnetics are a key. Magnetics kind of have a little bit of the copper and the MOSFET dilemma. There are certain things about a magnetics that aren't going to change. They're inherent to the material itself. But at the same time, there's a lot of room for innovating in terms of materials and coming up with better magnetic materials that represent lower losses, or better magnetic materials that can provide lower losses at higher switching frequencies and things like that.
Yeah, and it's interesting you mentioned higher switching frequencies, because it also makes me wonder, how we're manipulating our modulation approaches, for example, the kind of feedback from the circuit that we're collecting to make very timely reactions and adjustments. Do these sorts of things play in, or are they negligible when you consider just the raw physics of the components?
So, yeah, that's actually a great question. So the thing about high switching frequency is switching frequency actually goes all the way back to the copper dilemma, right? So again, we're not going to make copper more efficient. The way that we can essentially address that challenge is, can we make a power converter that uses less copper to move electricity from input to output? Can we make a converter smaller and more efficient? Because if you think about, for example, a winding around an inductor or a transformer, the length of that winding is copper. The length of that winding is directly proportional to the resistance that will have. And the resistance is essentially a physical element that we can't change. We can't change the resistivity of copper, but if we can make that inductor or that transformer smaller, we can make that length, the path length of that winding, shorter. And by doing so, we can make a system that has less resistive loss, even though we're still using the same material to carry the electricity. High switching frequency is key to being able to make a smaller converter, because if you switch to higher switching frequency, your energy storage elements like your transformers and inductors and anything that holds kind of inductive energy can shrink. And capacitors factor in there as well. Higher switching frequency and being able to shrink things means being able to make them smaller, which means being able to use less copper and have less resistive losses. The trade-off to higher switching frequency is that the higher that you switch in frequency, the more switching losses you incur by turning on and off your MOSFETs at a faster rate. Any gains that you have in terms of smaller parts can quickly be given back if you're pumping a lot of switching losses into the system. And that's why, Vicor looks at control technologies and topologies that promote zero voltage and zero current switching. Because if you can limit or eliminate switching losses in your power converter, now you've solved this trade-off between switching frequency and switching losses. Now you're able to make things much smaller and get the benefits of efficiency. That's a perfect example of the kind of trade-offs that you face in the power electronics world.
Absolutely. With different frequencies, do you find that noise either is exacerbated or minimized at certain frequency ranges, or is it just switching noise that exists irrespective of frequency?
So certain types of noise, for example, when you're zero voltage, another term for zero voltage and zero current switching is soft switching. I guess part of the physics behind that is that if you're hard switching, the way that you keep your switching losses as low as possible is you essentially turn your switch on and off as quickly as possible. In other words, if you think about a MOSFET as a variable resistance, when the MOSFET is fully on, the resistance is extremely low, you have very low loss. When the MOSFET is off, there's no current flowing, resistance is very high, there's zero loss there. It's that in-between time where the MOSFET is transitioning from one resistance to another that most of your losses occur. So if you're hard switching a device, if you're not zero voltage or zero current switching, you want to transition through that region as quickly as possible. Anytime you take something electrical and you shoot the voltage or the current very rapidly from one point to another through inductance and parasitics within the circuit, you essentially shoot energy into other areas of the system. That's essentially the genesis of electromagnetic interference or conductive noise. By definition, if you're hard switching something, you're going to have more noise associated with it. When you're soft switching something, you don't, first of all, if there's 0 volts across it, you don't need to very quickly change the voltage of the current. Because essentially at that point, at that 0 volt point, if there's no voltage, there's no current that's being forced through that variable resistance. That's probably a slightly simplified way of looking at it, but I think it's actually quite accurate. So by essentially soft switching, what we're really saying is we're really talking about slow switching something. And when you slow switch something, you don't have that parasitic spike of voltage or current that squirts into other areas of the system and causes noise. That's not to say that any soft switch converter has absolutely no noise. I mean, there are other sources of noise. But if you take, kind of a hard switch converter and a zero voltage switch converter, and you look at the noise signature from the two converters, you're going to see a big difference just by what results from soft switching versus hard switching.
Electrification is changing how we drive. Hybrid and electric vehicles are becoming more efficient, reliable, and cost-effective for consumers. But these changes come with challenges, such as functional safety and even changing fleet architectures. Texas Instruments is here to help. Whatever your design requires, TI has the products, tools, and system solutions to help you get the job done. For more information, please visit www.ti.com/powertrain.
One thing you mentioned earlier in the conversation is power quality. What sorts of power quality issues are you solving for, whether at Vicor or just in general as a power management engineer?
Yeah, so I think there's a number of different things that apply to a number of different industries. When I am referring to power quality, I'm essentially referring to probably a number of different things. One of those things is EMI, how clean is the power when you turn on, when your power converter is working, how much noise is coupled into your radio, or how much noise is interfering with the Wi-Fi signal, or things like that. Just really important aspects for functionality of the rest of the system. But what I'm also referring to is basically the load's ability to handle variations in voltage. Going back to our earlier conversation about where does the line between converting down from 48 to 12 versus simply having your 12 volts distributed throughout the system, where does that line drawn? And one of the things is basically just as you increase the amount of current that you're distributing through a system, the power quality gets worse. There's a lot of benefits to being able to have a stiff voltage source. And one of the focuses in power quality is being able to develop a system that provides a very stiff voltage source that can handle whatever kind of slew rate the loads provide on it. So for example, just stepping away from automotive for a second and looking a little bit at the computing side of things, microprocessors require a voltage source that can handle tens of thousands of amperes change in microseconds.
Right.
That kind of a slew rate requires an extremely low impedance at extremely high frequencies. And the difference between having a voltage deviation of 70 millivolts to a load step versus 75 millivolts may be the difference between having a working processor and having a blue screen of death. Power quality is very important in those kinds of situations, that you can have a power source that can power whatever load or whatever transient the load might throw at it.
My follow-up question to that would be the thermal management that has to go along with being able to manage such a dynamic load. So in the case of the modules that you're producing, that's again another great example of how do they squeeze that much performance into something so compact and lightweight and not have sort of the thermal issues that plague so many systems?
Okay, good. That's a good question. So I think there's probably two elements to that. One element goes back to size. The smaller you can make something, the closer you can put the source of the heat to essentially a surface that can allow that heat to be conducted away from the device. So you think about a power supply that has, that's housed in a gigantic box, and the MOSFETs are kind of buried inside that box on a printed circuit board. You need to attach them to a heat sink, and then you need to have a fan that blows air across that heat sink to get the heat from those MOSFETs out. If you look at how we at Vicor have shrunk our power components to the smallest possible size, we now have fractions of a millimeter between the MOSFETs that are processing the power and the surface of our packages or our components. The second one is kind of I guess you could say the motherhood in apple pie, which is if you make a more efficient power converter, there's less heat that you have to remove in the first place. So that's the other and somewhat more straightforward way of solving a thermal problem is by reducing your losses to begin with.
Right. It strikes me that the real strong case for going for something like a module seems like you no longer have to be somebody with a lifetime of expertise in order to get a very stiff, responsive, and very clean power source. The second piece of that, though, is the fact that this thing has to get through certain certifications. It seems like that would be an advantage, too. If you're a design engineer, you buy a module, and all of those lifetimes of design expertise have been kind of baked into the module, and it's certified. So it starts to look like a very attractive proposition.
Yes. Yeah. I mean, the way I like to look at it, or the way I like to think about it is that we're not the engineers and our customer, we're not trying to take away their job. What we're trying to do is we're trying to solve and very effectively solve power challenges that otherwise they would be on tap to solve on their own. And so rather than reinventing the wheel, the customer can focus on their unique challenges that they have in their system and not have to worry about the power conversion challenges that can be solved essentially at a global level and really apply universally to various systems. And you're absolutely right. An automotive power supply is going to have a different standards that are going to need to be met compared to a microprocessor power supply or a robotic, industrial robot power supply. Those standards are going to be different, and those standards are going to be industry unique. But to the extent that all three of those industries requires a voltage, a current, and a certain level of power, certain level of power quality and cleanliness and stiffness, let's solve those global challenges kind of across the board, and then allow the customer to focus on challenges that are unique to their system and their industry.
Once again, a sincere thanks to our guests Milovan Kovacevic and Paul Yeaman, who joined us this week from their home offices to make me a little smarter about power electronics. We will continue to explore this broad topic in subsequent episodes, and so we want to hear from you. What questions do you have about power electronics engineering? Do you tend to go for drop-in modules for power supplies, or would you prefer to design your own converters and regulators? Connect with me on LinkedIn or leave your comments on this episode's page on allaboutcircuits.com. And if you enjoy Moore's Lobby, please take a moment to leave us a review and to subscribe wherever you listen to this podcast. It's a small gesture that really does go a long way in helping us to build a meaningful community of listeners and contributors. Thanks for listening.